So let's move to lecture 17D2, okay, B part 4, Noether theorem. This is the final 2. Now, from the last lecture, 17D1, you see the variation of the action, okay, is written as the integral of the volume, or this quantity over here, dx3. Attention now, we are now developing for R3. You see the 3 dimension. So then you can write from the, attention now, the Gauss theorem, you can relate the volume with the boundary. See? And this is equal 0. Why? Because the invariance of the symmetry means invariance of S, symmetry of S. Then I plug delta S is equal 0. This is 0 over here. So this is from Gauss' theorem. I can write this. Now, this equal 0 means invariance of the action, because we are assuming the symmetry, the context of symmetry. Then, because this is true for arbitrary delta xj, this case, in the interior, we conclude that this partial derivative over here is equal 0, where qj is the Lagrangian xi delta xj. You see, that's a very important issue over there. So we typically assume that this delta xj at the boundary is equal 0, so that first we avoid having to worry about what happened at the boundary. So this will be also applied on the interior. So it's a technical condition that allows, in this case, the derivation to focus on local conservation. In field theory, this is analogous to this case, to requiring this delta phi is equal 0 on the boundary. Now, in this case, we require this just to apply, okay, the variational principles. You always use this condition over here on the boundary. So, attention now. Observe that delta xj on the boundary is equal 0, since delta xj at the boundary different from 0, but Lxi could be 0. What I'm calling attention here is this. So you look at it, look how easy, okay? You see that. You just look at here, okay? So this is equal 0, okay? Does not imply necessarily that delta xj on the boundary be 0, because Lxi could be 0. You see? That's clear what I'm saying. So that's what I wrote here. I can have the situation in which this is different from 0, but this is 0. It still fits, okay, what is with over here. Now, that's why we assume, this boundary here to be 0 also at interior, okay? So there is no question. We are assuming this, then assuming that as a boundary condition, obviously this integral here on the boundary will be 0. See, because this is assumed to be 0. See? But what I'm saying is this is equal 0 does not imply necessarily that delta xj will be 0. See, that's important issue here. Delta S is equal 0 since it's invariant, okay? Then I set 0 here. But the boundary condition, I impose the delta xj on the boundary will be 0. Attention now, independent of this is equal 0. Because again, Lxi could be 0 and this be on the boundary any value. But the hypothesis is delta xj is equal to 0, including the interior. See, that's important here. Okay, in physics we typically want to derive local conservation. In this case, local conservation laws, you see, we obtain from global symmetry. Global symmetry, you see. So this ensures we want to say that if a total divergence integrates to 0, again, over any region, then this condition over here will be 0 pointwise. What is Qj? You just look at here. Qj is Lagrangian of xi delta xj. See, that's important here. Now, then, that's why in the standard Noether theorem, we assume that delta xj on the boundary is equal to 0. You see? Because, again, I'm repeating this because it's confused. Because you see here, okay, this is 0, okay? The integral is 0. So this could be 0. You see? This is different from 0. But I assume independent this to be 0, then you satisfy that relation, okay? This will be 0 on the boundary. And also is valid for the interior. So then you recall that relation here, and for the next lecture, okay, it will be, in this case, lecture lecture 17 D3. You see, just to remember clearly that xi represents this argument over here. You see, that's this annotation just to simplify this argument here of L. You see, now we will start from here just to go. Our goal is the Noether theorem. See, that's important here. The next lecture, D3. Okay, that's it.